Alright, hello class. In this video we're going to be looking at still cylindrical and spherical coordinates, but today in this video we'll be focusing on the spherical coordinates. And it's very similar in concept to cylindrical coordinates. What's happening on the xy plane is exactly the same. It's still polar coordinates on the xy plane, except how we get to the point itself, right, in 3 space, how we get our height is done differently. We use another angle to get our height, much like we did in polar coordinates. So in polar coordinates, if you remember, instead of doing xy, like rectangularly, what we do instead is take an angle and the distance to the origin. We're doing the same thing. We take an angle theta on the xy plane, angle phi from the positive z-axis, and once again a length from the point we're talking about to the origin. Okay, so to give a more closely described version of this, we still have our theta on the xy plane, okay, but to get up to the point, right, up in 3 space, now this could also be going down into the positive or negative z's, to get to this point, what we do instead is we determine what angle we need on the xy plane, and then we take the distance from the origin to this point, okay, and then we designate that by the angle from the positive z-axis. Okay, so now this distance, we use the Greek letter for r, which is rho, which kind of looks like a p, and this is how we get our new transformation, our new way of talking about these points. Okay, so the new transformation is essentially polar. Okay, but instead of a plus z, it's a plus phi and rho. So we use a new angle and a different distance. Okay, so how we're going to determine this transformation is we're not going to go from Cartesian to spherical, because that is a real pain. What we're going to do instead is we have our x, y, and z. Okay, we're going to go from r theta z, and then instead of going straight from x, y, z into spherical, we're going to do our theta, phi, rho, but we're going to get that from cylindrical, almost called it polar, which, you know, essentially the same thing. So we're going to go from r theta z into theta phi rho, and doing it this way, right? Doing it this way, we will actually get a formula that will let us go straight to it. But this is a much easier direction to understand, okay? Because really, we're creating this in the same way, but instead of just taking a z, adding a z to it, we're instead determining it. I mean, it's the same z, but we're determining it instead by the hypotenuse of this right triangle that we've just made. Okay, so here we have, I've sort of colored it a little differently here, but we've created basically a right triangle that's been, say, revolved somewhere else. Okay, so if we, say, transfer this over here, okay, and look at it from the side, what we essentially have here is a right triangle. Right triangle whose base is r, its height is z, and its hypotenuse we are calling rho. Okay, and the angle here is phi. Now if this angle is phi, and this in purple is also a vertical line, okay, and say we continue this red line out, okay, Okay, based on these two things here from our basic geometry, that's going to make this also phi, and then this phi. Okay, so we now have phi up in this corner, and so now we can actually start creating some trig. For phi, if I think about sine of phi, okay, sine of phi is the side opposite over hypotenuse. So the opposite side of phi is r, and over the hypotenuse, which is rho. Okay, so what this gives us is that r is equal to rho sine phi. Okay, and then if we instead look at cosine of phi, well, cosine of phi is adjacent over hypotenuse, so that's going to be z over rho, which then gives us that z is equal to rho cosine phi. And these are the pieces that are going to build our transformation for us. Okay, because what we're doing is we're moving from r theta z into theta phi rho. And I guess I should have matched these, but it really doesn't matter that much, honestly. Some math professors may tell you it does, but in my experience, it doesn't really. So what we're doing, again, is we're moving from, let's say, r theta z into theta phi rho. All right, and we're going to use this transformation. Specifically, we have that r is equal to rho sine phi. Okay, z is equal to rho cosine phi. All right, and then theta, well, it's the same theta, so theta goes to theta. All right, so that makes this a really nice transformation, just like we had before with z going to z. Okay, that's why I like to use this direction instead. But it is going to allow us to go from x, y, z, which I'll explain in just a second. Okay, now we also need to talk about this r dr d theta dz. Okay, that's going to go to, well, r we know is rho sine phi. Okay, and then it will be times the Jacobian in terms of theta phi rho, and then it will be d theta d phi d rho. Now this is not necessarily the order that we have to go in, but that part doesn't matter that much. Okay, so we need to find the Jacobian of this transformation. All right, so the Jacobian of theta phi rho is going to be the partial derivative of r theta z with respect to theta phi rho. Okay, so I'm going to set this up in a very specific order to make this easier to deal with. And you might be wondering what I'm talking about, but I'm going to, in this top corner, put theta in terms of theta. So the derivative of theta with respect to theta, that's going to make that 1. Then theta with respect to phi, then theta with respect to rho. Okay, then I'll do phi with respect to theta. Sorry, wrong one, sorry. It should be r with respect to theta, r with respect to phi, and r with respect to rho, and then we'll do z with respect to theta, z with respect to phi, and z with respect to rho. Okay, so let me move this down so we still have our transformation up here. Okay, and now we're just going to go through, and the reason I did it this way is you'll see theta with respect to theta is going to be 1, and theta with respect to anything else, phi or rho, will be 0. So we have a nice 1, 0, 0. Okay, and then we'll go through r with respect to theta. Well, r is not in terms of theta, so it will be 0. And z is also not in terms of theta, so its derivative will be 0 here. So what we've created is a matrix with a 1 in the corner and 0 for the rest. So really, this is just going to be a determinant determined, pun not intended there, by this part of the matrix here. Okay, because we'll get 0 for the other column, so it doesn't really matter what happens past that point. Okay, so now r with respect to phi. Well, r with respect to phi, that's going to be phi, rho cosine phi, and r with respect to rho will simply be sine phi. Okay, then z with respect to phi will be negative rho sine phi. Okay, and all right, and now z with respect to rho is just going to be cosine phi. Oops, not theta, phi. Okay, so there is our setup, and I don't even need to copy down the next columns because what we'll end up with is, for the first part, it's 1 times the main diagonal and negative the opposite diagonal, so it's rho cosine squared phi plus rho sine squared phi. Okay, but for the next pieces, it's plus 0 times, well, it doesn't even matter, okay? Then plus, well, we have another 0, and then it doesn't even matter. Okay, so we set this up in this particular way specifically so it would work out like this. Much easier to take 3 by 3 determinants if you can get like the top row mostly zeros. Okay, and here we have rho cosine squared plus rho sine squared. This is going to come out to be rho. Okay, so the Jacobian here is rho. But notice we already had rho sine phi because we had r dr. So that r is what becomes the rho sine phi. So the r becomes rho sine phi, and the Jacobian, well, that is equal to rho. Okay, so what we actually end up with as part of our transformation now is the r dr d theta dz goes to rho squared sine phi, okay, d theta d phi d rho, and again, it doesn't have to be in that order, but this is the part that's important right here. Okay, now from here, here's our important piece of the transformation. We also have, from here, we can now do x into this. Okay, so as I mentioned up here, we can do x, y, z into r, theta, z, and then into theta, phi, rho, and we do it like this. Okay, we do it like this. So from our polar coordinates, we know that x is equal to r cosine theta, and y is equal to r sine theta, and then that z just goes to z. Okay, but now we're going to, and let me use arrows here instead. And now we can get from here to our spherical coordinates by replacing the r's and the z's. So we know from what we just did that r, okay, is rho sine of phi, and z is rho cosine phi. Okay, move that down here. And so if x is r cosine theta and r is rho sine phi, then all we need to do is just change the r. Okay, so the r I could rewrite as rho sine phi, but leave the cosine theta alone. Okay, and we can do the same thing for y. Y is r sine theta, but r is rho sine phi, and we just leave the sine theta alone. And then with z, well, z, we just have its own little rho cosine phi. Okay, and same idea, dx, dy, dz, well, that goes into r, dr, d theta, which then will just go into rho squared sine phi, d theta, d phi, d rho. Okay, or d rho, d theta, d phi, or it doesn't matter. Typically, we'll do d rho, d phi, d theta. Okay, that's usually the order we'll go in, but often it doesn't really matter that much. Okay, so this is actually the transformation to go from Cartesian straight into spherical. I'll tell you, I don't actually memorize this exactly. What I do instead is I just remember that x goes to r cosine theta, y goes to r sine theta, z goes to z, then r goes to rho sine phi, and z goes to rho cosine phi. Okay, and then I just put those together. So once again, if you know polar, you know what we're doing here. Okay? The nice thing about this, though, is because we also get from here that if we have x squared plus y squared plus z squared, we put all these together, okay, that's going to be rho squared sine squared phi cosine squared theta, okay, plus rho squared sine squared phi plus sine squared theta, okay, then plus rho squared cosine squared phi. When we go to simplify this, we'll notice here in the first term, the cosine squared and the sine squared theta have the same thing sitting out front, right? So we can simplify this. So we can actually factor that out to get rho squared sine squared phi, okay, and I'll put it as times cosine squared theta plus sine squared theta, okay, and then this part stays the same. But this is 1. So this actually becomes rho squared sine squared phi plus rho squared cosine squared phi. Oh, and these two together now, well, that just gives us rho squared. Oh, well, that should make sense because if we remember what rho was the distance between whatever point we were talking about, say x, y, z, it was the distance between that point and the origin. Well, if we think about this in terms of the magnitude of the vector, the distance of rho should be the square root of x squared plus y squared plus z squared, giving us that rho squared is x squared plus y squared plus z squared. All right? So that actually gives us this transformation here, along with the fact that rho squared is equal to x squared plus y squared plus z squared. Okay, so for spherical solids, just like with cylindrical solids, even more so actually, I always want you to think solids of revolution. Okay, that's what I want you to think about. Okay, so if we want to do, let's say we want to generate the unit sphere. Okay, so here's how we're going to do it. I want to look at, just like we did before. Okay, you can think of this as the RZ axis. Okay, now if I want to generate the unit sphere, what I want is I want to take this semicircle, right, of radius 1 and rotate it around a full rotation. Okay, so how do we get this full semicircle? Well, remember, we're going to think of it in terms of our phi, because phi we're going to let go from 0 to, now we have to be careful about this, pi. So here's some conditions that I should have mentioned earlier on our limits of integration and how we think about this. Okay, phi is trapped between 0 and pi because it's made from, and this is the angle from the positive z-axis. Okay, so the reason it only goes from 0 to pi is because if we went any farther, right, if we went farther than pi, we'd be flipping around further this way, and if we rotate this, we're going to get a lot of extra stuff. Okay, so it's not the only way that we, would do this, but it's the way that we've essentially decided is the best way. Okay, then theta follows the same thing it did before. If theta is between, say, alpha and beta, we just want beta minus alpha to be less than or equal to 2 pi. Okay, and similarly, phi, or not phi, but rho is always greater than or equal to 0. Okay, so if phi goes between 0 and pi, okay, that means, well, here's phi equals 0, and we go all the way down to phi equals pi. All right, that gives us the full rotation. Okay. Then we want rho to be between 0 and 1. Right, so here's rho 0 out to rho equals 1. Right, so we want to map it down. And if we want the full unit sphere, then we're going to let theta give us the full rotation, 0 to 2 pi. So that rotates this around all the way, and then we get the unit sphere. Okay? What's really nice about this is we can, just like we did with cylindrical coordinates, we can make all sorts of crazy solids by altering this. So we could create a spherical shell by just letting rho go between like 1 and 2, for example. Okay, so for example, let's say these are our limits. Now how we visualize this is I always start on the RZ axis. And again, there are many ways to do this. I'm just showing you the way I like, and most of the time the way I like tends to be the simplest way. Just that comes from practice, from doing this a lot. Okay, so we're going to start with phi. Phi goes from 0 to pi. So here's phi equals 0. Here's phi equals pi. Okay, so it's the full rotation. Right, now we're going to look at our rho. Our rho is 1 to 2. So wherever we might be, here's rho equals 0. Let's say this is rho equals 1 and rho equals 2. Okay, so we're basically creating a semicircle disk here. Okay, so here's our disk. Here's all our different rows that we're rotating down from 0 to pi. And then theta tells us how much to rotate it around the z-axis. Okay, so that tells us, all right, we're doing the full rotation. So what we've created here is essentially, it's very hard for me to graph, but it's essentially a, we took a sphere and hollowed out another sphere. So this is a sphere of radius 2 that has a sphere of radius 1 removed from it. This is called a spherical shell. Okay, and we were able to create it with just constant limits in spherical coordinates. That's the beauty of spherical coordinates, is that we can create really complicated objects using constant limits. Okay, so let's take a look at this example here. Let's evaluate the triple integral over d, x squared plus y squared plus z squared to the negative 3/2 dv, where d is the solid between two spheres of radii 1 and 2 centered at the origin in the first octant. Okay, so I know I want to use spherical coordinates here partially because of this guy. This x squared plus y squared plus z squared I know can become a rho squared. And we're talking about spheres here. We're talking about this solid between two spheres. That's really a spherical shell. Okay, with inner radius 1 and outer radius 2. So that actually tells us our limits on rho really quickly. Okay, so our rho is going between 1 and 2. Now, how we find our other limits is centered at the origin. Okay, that, that's hopefully always true, but in the first octant. So first octant means that where x, y, and z are all greater than or equal to 0. Okay, so if we think about this in terms of the ZR axis or RZ axis, okay, the first octant is basically the first quadrant, looking at it from this side. So what we want is, well, if we're talking about a spherical shell, it should look something like this on this plane. Okay, right? And we should only revolve it so that it stays above the first quadrant. So if this is, let's change this now to y, okay, and this is x, we only want this revolved this far so that we can stay in the first octant. Okay, so that tells me, looking at this, and let me quickly go back to RZ. Okay, RZ, we're only taking the top quadrant, so this should be phi trapped between 0 and pi over 2. Okay, and then on the xy plane, and I'm just showing this in case you don't feel comfortable just graphing this in 3D, but on the xy plane, we want our theta to only be in the first quadrant. So our theta should only go between 0 and pi over 2 as well. Okay, these two limitations on our phi and theta are going to give us a region only in the first octant. Okay, and so now that we have this, our integral should pretty much follow, right? I'm going to put theta on the outside, so I want theta to go from 0 to pi over 2. Right? I want phi in the middle, so I'm going to go from phi equals 0 to phi equals pi over 2. And I'm going to put rho on the inside, so rho goes from 1 to 2, right? Not too bad, hopefully. Then I'm going to change this to be rho squared to the negative 3/2, then rho squared sine phi, right? So remember, that's our like Jacobian stuff that pops up. Then it's going to be in this order, d rho, d phi, d theta. And now, well, we have it set up in an integral that we can actually do. Okay, this will simplify to be rho to the negative 3. And so rho to the negative 3 times rho to the 2 is rho to the negative 1. Okay, also known as 1 over rho. Okay, sine phi, d rho, d phi, d theta. And now, integral of 1 over rho with respect to rho is the natural log absolute value of rho. All right, so we get natural log rho, and we're just going to use the fundamental theorem of calculus from rho equals 1 to rho equals 2. Thankfully, rho equals 1, natural log of 1 is 0. So this comes out to simply be, okay, the integral from 0 to pi over 2, the integral from 0 to pi over 2 of the natural log of 2 times sine phi d theta. Now we just integrate with respect to phi, and it's just the integral of sine phi, right, which is going to be negative cosine phi. All right, so we get the integral from 0 to pi over 2 of negative ln2 cosine phi, phi ranging from 0 to pi over 2 d theta. All right, so now we'll just plug and chug with our limits here for phi. And this is, again, why I like to write the limits over and over again. So when I get to here, I know exactly what I'm plugging into. I guess in this case it doesn't matter that much, but it's here that cosine of phi will be 0. It will be 0 at the top limit. Okay, so we'll get the integral from 0 to pi over 2 in theta, negative natural log of 2, and cosine of pi over 2 is 0 minus cosine of 0, which is 1. Okay, so we get right back to a positive again. So now we have the integral from 0 to pi over 2 of the natural log of 2, and thankfully we're finally integrating a constant, so it will be the natural log of 2 times pi over 2 minus 0. So let's write this as pi ln2 over 2. Right, and that should be good enough for government work. All right, let's take a look at another example here. Let's evaluate the triple integral over d of e to the negative x squared plus y squared plus z squared to the 3/2 over the top half of the unit sphere. So when we're talking top half of the unit sphere, what we're really talking about here is sort of this part here. Okay, so no negative z's. Okay, so where z is greater than or equal to 0, but we're over the other, and we're all in the other octants. Okay. All right, so how we get the top half of the unit sphere? Well, since we don't want z to be negative, when we look at the RZ axes, we essentially only want to go from phi equals 0 to phi equals pi over 2. Right? That's where z is positive. Okay, now unit, if we're talking about the unit sphere, that tells us that we want phi going from 0 to 1. Okay, so something like this. And that's what we're spinning down. But we only want the top half of the sphere, so we can actually spin this around the whole way. Okay, and that will give us the top half of the unit sphere. So that tells us that we want our theta to go between 0 and 2 pi, a full rotation. Okay, so we want a full rotation around the z-axis, but we want only half of our phi. Okay, so that means we have these limits of integration. Phi going from 0 to pi over 2, theta going from 0 to 2 pi, and rho going from 0 to 1. Then from here, just like before, this x squared plus y squared plus c squared is going to become rho squared. Okay, so then we get the following integral. Again, I tend to use theta first. That's typically the way we do it. Theta going from 0 to 2 pi. Phi going from 0 to pi over 2. And z going from, not z, I'm sorry, rho going from 0 to 1 of e to the negative rho squared, and then we need our dv to become rho squared. Whoops, sorry, forgot this part. It's negative rho squared to the 3 halves. Then the Jacobian part, the dv, becomes rho squared sine phi, then d rho d phi d theta. Okay, and once again, this 3 halves is going to make this rho squared to the 3 halves into rho cubed. Okay, so let's simplify this down. Okay, so we have the integral from 0 to 2 pi, the integral from 0 to pi over 2, the integral from 0 to 1 of e to the negative rho cubed times rho squared sine phi d rho d phi d theta. So here we can, in terms of rho, do a quick u substitution, because when we divide by the derivative of the inside here, the rho squared should cancel. So let's see. Okay, so the integral of e to the stuff is itself. Then we just divide by the derivative of the stuff. So that should be negative 3 rho squared. We'll keep this rho squared here, and as we can see, those rho squareds cancel, and we'll evaluate this from rho equals 0 to rho equals 1, and then we'll leave the rest of this alone. Okay, so now what we have is basically negative 1/3 e to the rho cubed. Now when we plug in 0 to rho cubed, that will zero that out. And when we plug in 1, we should get e to the negative 1. Okay, so we'll get negative 1/3 e to the negative 1 minus a negative 1/3, so plus 1/3 e to the 0. Whoops, messed that up. Okay, times sine phi d phi d theta, and we can simplify this. Right, I'm going to factor out the 1/3, and this is 1, and I have 1 minus 1 over e. Okay, times sine phi d theta. All right, so now this is just a constant, so really we don't have to worry that much about it. We can move it outside if we like, or just leave it alone. Now we're going to integrate with respect to phi, right? And all we have is the sign, so we'll once again get a negative cosine phi. Okay, so I brought the negative out here, so I have negative 1/3 times 1 minus 1 over e cosine phi, and we're going to evaluate this from phi equals 0 to phi equals pi over 2, and we have the same idea here. The cosine of pi over 2 is what goes to 0, but the phi equals 0 is what goes to 1. Okay, like so. So this will be this constant times 0 minus 1. So that's going to make this positive again. Right, and we're just integrating a constant. So we just take the constant and multiply by the difference of the limits. So that will just be 2 pi So we could say this is 2/3 pi times 1 minus 1 over e, and just leave it like that. All right, so one of the last things I want to mention, you may have seen it in the homework, I haven't really mentioned it yet because it's not a huge deal. Basically, you can use triple integrals to find the volume of a solid by basically integrating 1. Right, so if you take the triple integral over some solid of 1 dV, this actually equals the volume of S. Okay, now often, you know, the book uses it as just an example, gets you practice setting up limits. A lot of times it's not all that useful, but it can be when we start talking about different coordinate systems and really funky regions. So for example, take this particular solid. Okay, so for example, let's find the volume of the solid within the sphere of radius 3, or phi is trapped between pi over 4 and 3 pi over 4. So the reason we would want to use a triple integral here really stems from the fact that if you think about what's happening here, this is the RZ plane. Okay, here's phi equals pi over 4, and here's phi equals 3 pi over 4. All right, so we're only looking at values between here. Okay, and let me make this a little better. Right, if we think about our phi, if we're talking about radius 3, say this is 0 and 3 for our rho. This weird looking shape here is what we are rotating around. So it's almost like we take a sphere and we are removing, we're like boring out, like say we take a drill, a conical drill, and drill into the top and the bottom until they meet. And this is the weird shape that we've created. Okay, it's a solid of revolution. However, trying to find the volume of this using a double integral and finding, say, some z functions to find this with would be a real nightmare. Right? Instead, we can use the triple integral of 1. So instead, the volume equals the triple integral over d of 1 dv. Well, we just need to make sure that we set this up over spherical coordinates. Okay. All right. So since we're doing a full rotation in theta, that tells us that theta is between 0 and 2 pi. Okay. We're actually told what our phi should be between. It's between pi over 4 and 3 pi over 4. Okay, and rho, well, rho, we're talking about radius going from 0 to 3, so that's, once again, just 0 to 3. Okay, now we're just integrating 1 times rho squared sine phi d rho d theta. Whoops, sorry, I'm totally messed that up, didn't I? Those are phis. Sorry about that. Okay, so d rho d phi d theta. Okay, so notice that this comes along with the Jacobian, this comes along with dv. So even though we're integrating 1, this still comes from dv. All right, so never forget that. So it's not as simple as integrating 1. However, you know, it's not that bad. It's way better than trying to set this volume up with a double integral. All right, and from here, well, these outer integrals don't change, and it's going to be we're integrating with respect to rho, so we'll get 1/3 rho cubed. And we are going to evaluate that from rho equals 0 to rho equals 3. All right, and then we still have our d phi and our d theta. Okay, now when we plug in the 3, we'll get 27 divided by 3, so we should get 9 minus 0. So we end up with the integral from 0 to 2 pi, the integral from pi over 4 to 3 pi over 4 of, when it's all said and done, this will just be 9 d phi d theta. And whoops, I totally forgot that we should have a sine of phi here. Okay, d phi d theta. Okay, now we're going to integrate with respect to phi, and so we get the integral from 0 to 2 pi, from pi over 4 to, we're integrating that, so it's just going to be negative 9 cosine phi, evaluated from phi equals, let me do that in the purple, phi equals pi over 4 to 3 pi over 4. Then we have the d theta on the outside. And so with our fundamental theorem of calculus going on here, I'll have negative 9 cosine of 3 pi over 4 minus a negative 9, so plus 9 cosine of pi over 4, and we'll have a d theta. All right, so this is quadrant 2, right? And this is quadrant 1. So cosine is positive in quadrant 1 and negative in quadrant 2, so this will be a negative, negative. So we're going to get the integral from 0 to 2 pi of this will be 9 root 2 over 2 plus another 9 root 2 over 2 d theta. So 9 halves plus 9 halves will come out to just be 9. So we'll have the integral from 0 to 2 pi of just 9 times the square root of 2 d theta. And now we're just integrating by a constant, so we'll get 9 root 2 times 2 pi minus 0, or 18 root 2 at the end. Okay, so that's that, and that's really all there is to talk about spherical coordinates. Yes, they are a bit brain melty. I do admit that and know that. However, as long as you think about it as the way I suggested, think about it in terms of solids of revolution. Theta tells you how much you rotate that shape that you have to make that solid. And hopefully that can help you, figure this all out. So that should get you rolling on homework, and I'll see you all in the next video.